Welcome to The Explainer. So today we're going to crack open a scientific paper from way back in 1981. Now, I know it might look a little dry, but trust me, it's basically a detective story that completely changed how we make one of the most important materials on Earth, steel. The answer isn't just about mixing some iron and carbon together. Nope, it's all about a hidden transformation, a secret that happens deep, deep inside the metal itself. And it's a process that scientists have spent decades trying to master. At the very heart of all this is something called the martensitic transformation. Honestly, you can just think of it as steel's superpower. But here's the catch. To control this power, to really harness it, scientists first had to figure out how to measure the invisible energy that triggers it all, what they call the driving force. Okay, here's our game plan. First, we're going to dig into the secret power of steel. Then, we'll meet the competing theories that were trying to explain it all. After that, we'll look at the hard evidence, see how a new approach finally cracked the case, and get the final verdict. Let's do it. So yeah, before you can even think about designing the perfect alloy for, say, a jet engine or a massive bridge, you absolutely have to be able to predict exactly how much energy it's going to take to kick off this incredible transformation. This coiled spring analogy? It's pretty much perfect. For decades, the biggest puzzle for metallurgists was this. How do you get an accurate number for this driving force? Because if you get it wrong, all your predictions are just off. But if you get it right, well, then you unlock a whole new level of designing materials. And that challenge, as you might guess, led to a real scientific showdown. By the early 1980s, you had several competing models, different theories, and each one had its own special formula for calculating that all-important driving force. So in one corner, you had the old guard, the established methods from guys like Fisher and Bell. And in the other corner, you had a newer, more theoretically polished approach called the LFG method. The big question on everyone's mind was, which one actually worked in the real world? So how do you settle a scientific argument like this? Well, the author of this paper did what any great scientist does. They went straight to the hard evidence, the actual experimental data. Now check this out, because this slide is basically the entire investigation in a single picture. Each one of those little circles, that's a real-world measurement. Each solid line, that's a prediction from one of the theories. The goal is super simple. Find the line that best connects the dots. But, as you can probably see, it wasn't that simple at all. The old models, like that Fisher curve way up at the top, they just weren't cutting it. They were plagued by what the author calls interesting effects, which, is basically polite scientist speak for weird results that don't make sense and are driving us crazy. And this is where the detective work really starts to pay off. Because if you look closely at that chart, one of those lines, the curve for the LFG method, it tells a much, much more consistent and believable story. So why did this LFG method stand out? Well, the critical thing to understand is that it wasn't just a lucky guess. It was actually built on a more solid theoretical foundation. It had a better way of modeling how carbon atoms really behave inside the iron. It was, as they say, theoretically reasonable. And it showed something huge. The driving force didn't actually change that much with carbon content, which is what everyone else thought. And this right here just illustrates the breakthrough perfectly. I mean, look at that highlighted curve. See how it just elegantly traces the path laid out by the actual data points? It's not a perfect match, nothing ever is, but man, it captures the real-world trend way more accurately than any of the other contenders. So, after all that, what's the final takeaway? What's the verdict from this deep dive into the nitty-gritty science of steel? The verdict was in, and it was pretty clear. This paper from 1981 basically settled a major debate. It showed that the LFG method was a much more reliable way to calculate that hidden energy, proving that the driving force was way less sensitive to carbon than everyone had previously thought. And listen, this isn't just some dusty academic exercise. Getting the model right has huge, huge real-world consequences. See, accurate models give you precise predictions, and those predictions, they let engineers create what are basically designer steels, alloys with the exact right hardness for a surgeon's scalpel, or the insane strength needed for an airplane's landing gear. It really makes you think, doesn't it? Our modern world is, quite literally, held up by the quiet resolution of thousands of complex scientific arguments just like this one, all hidden away deep inside the materials we rely on every single day.